Hello everyone. In today's lecture, we'll continue our journey with designing IIR filters. In the previous lecture, we've seen that in order to design an infinite impulse response filter, we first need to transform the discrete time filter specification into a continuous time filter specification. And the second step was to design a continuous time filter or an analog filter such that it meets the specification we have. And we've learned how to design Butterworth filters. And the third step was to transform this continuous time filter into discrete time filter, which is the topic of today's lecture. So today we'll be talking about transformation of continuous time filters to discrete time IIR filters. There are many procedures that can be used to transform continuous time filters into discrete time filters. Two of them actually stands out. One of them is the impulse invariance transformation, which has limited applicability. It has certain limitations. That's why it's not widely used, but it has educational value. The second transformation is the bilinear transformation, which is universally applicable to many situations and it's most commonly used. But due to time limitations, we will only consider the second transformation, which is the bilinear transformation. Each transformation is equivalent to a mapping function, f of z. So we are looking for a function that would map the S domain into Z domain. Clearly, different procedures or transformations give rise to different filters, but these different filters should be meeting the specification we have. So we might be having different realizations of discrete time filters, but supposedly they should be having the same specifications. Any useful mapping from the S domain to the Z domain must satisfy three desirable conditions. The first condition is that if H continuous of S is a rational function, in other words, if it is a ratio between two polynomials, it should be mapped into a rational H of Z, that is a ratio between two polynomials of Z minus 1. And this condition guarantees that the digital filter will be realizable, because we will not be able to implement or realize a digital filter unless its transfer function is a ratio between two polynomials. The second condition is that the imaginary axis in the S domain, the j omega axis, must be mapped on the unit circle in the Z plane. That is, S, which is equal to j omega, or other words, sigma is equal to 0, for omega going from minus infinity to positive infinity, must be mapped to Z equal to e to the power j omega, or in other words, r equal to 1, for omega going from minus pi to pi. In other words, the imaginary axis, the j omega axis in the S domain, must be mapped on the unit circle. The third condition is that the left half plane of the S domain must be mapped into the interior of the unit circle in Z domain. In other words, S, which satisfies the condition real part of S is less than 0, this basically means the left half plane of the S domain must be mapped into a Z which is modulus Z less than 1, that is inside the unit circle. These two conditions, 2 and 3, guarantee that if the continuous time filter is causal and stable, then the digital filter or discrete time filter will also be causal and stable. In order to understand this, let's move to our whiteboard over here. This is the S domain, and this is the Z domain, and this was the unit circle. Now, if we have a causal and stable continuous time system, we know that all the poles would be located in the left half plane. So if this is pole number 1 and pole number 2, this system would be causal and stable because it has all its poles in the left half plane. And for any useful transformation from continuous time to discrete time, from the S domain to the Z domain, any pole happening in the left half plane, such as P1, must be mapped inside the unit circle, and pool P2 also must be mapped inside the unit circle. This way, the discrete time system would have all of its pools inside the unit circle, which is the condition for a causal and stable discrete time system. In general, we want all the left half plane of the S domain to be mapped inside the unit circle. This will guarantee that any pool happening in the left half plane in the S domain is mapped into a pool inside the unit circle. In other words, any causal and stable continuous time system is mapped into a causal and stable discrete time system. The second requirement is that the j omega axis, the imaginary axis over here, should be mapped on the unit circle. So if the j omega axis is the edge separating the left half plane and right half plane in the S domain, the unit circle is the edge separating inside and outside the unit circle. So the j omega axis must be mapped on the unit circle, the left half plane must be mapped inside the unit circle, and this guarantees that a causal and stable continuous time filter is mapped into a causal and stable discrete time filter. So, as we can see over here, the left half plane of the S domain is mapped inside the unit circle, the j omega axis is mapped on the unit circle, and any pools or zeros happening in the left half plane will be mapped into pools and zeros inside the unit circle. So any useful transformation must satisfy these three conditions. So the first type here is the impulse invariance transformation, which we will not go through. We will skip it because it has many limitations and it's not practically applicable. So we will move right away to the bilinear transformation. So, as we've said that the impulse invariance transformation has many limitations. To avoid these limitations, we will use another transformation which is called the bilinear transformation. The bilinear transformation is an invertible nonlinear mapping between the S plane and the Z plane. And this mapping is defined as follows. S is equal to 2 over TD 1 minus z to the power minus 1 over 1 plus z to the power minus 1. In other words, if we have a continuous time filter, replace every s with 2 over td 1 minus z minus 1 over 1 plus z minus 1. The parameter td actually has no effect in the design process, and we usually assign a value of 2 to td, so we will always set td to be equal to 2. This way 2 will cancel out with td, and we will simply be replacing s by 1 minus z minus 1 over 1 plus z minus 1. And we emphasize that td here does not have any interpretation, it's just a constant, because in the impulse invariance transformation we had a similar constant t, and at that situation it was a sampling interval. Here it does not mean anything, it does not involve any sampling operation. The mapping of the bilinear transformation satisfies the three desirable conditions we have said before, which makes this bilinear transformation most popular technique for mapping continuous time filters into discrete time filters. So the first desirable property was realisability, which means that a rational H continuous of S is mapped into a rational H of Z. Here we have a mathematical proof which we will skip. We will not go through this proof. It shows basically that a rational H continuous of S is mapped into a rational H of Z. So the bilinear transformation always gives a rational H of Z, and this bilinear transformation reserves the number of pools. So if we have n pools in the continuous time filter, we will be having n pools in the discrete time filter. So the number of pools is preserved. In other words, the order of the system is preserved. So if we have a third order continuous time filter, we will be having a third order discrete time filter if we use the bilinear transformation. But the bilinear transformation adds n minus m zeros. So zeros will be added such that the number of zeros in the new or the discrete time filter will be equal to the number of poles in the discrete time filter. In MATLAB, we have a command called bilinear which do this transformation for us. So let's try to apply the bilinear transformation in this example. We have a continuous time system, h continuous of s, which is equal to 5s plus 10 over s squared plus 7s plus 12. So given this system, we need to apply the bilinear transformation or transform it into a discrete time filter. The first step is to set TD equal to 2. This will always be the case. TD is just a constant. It does not affect the filter specification. It can take any value, and the easiest value is to set it to be equal to 2. This way 2 will cancel out with TD, and next we will replace S by 1 minus Z minus 1 over 1 plus Z minus 1. So every S in this expression will be replaced by 1 minus over 1 plus. So 5s will be 5 times 1 minus z minus 1 over 1 plus z minus 1 plus 10, and so on. And then you can do the simplification, not a big deal, and you can reach this final result. So h of z will be a second order polynomial in the numerator and a second order polynomial in the denominator. And here a few notes. The first thing, that the continuous time filter had 1 0 and 2 poles, and the discrete time filter here have 2 zeros and 2 poles. So the number of poles is preserved. We had a second order continuous time system which was mapped into a second order discrete time system. But the number of zeros has been changed. It was 1 0 in the continuous time filter, now it's 2 zeros in the discrete time filter. The bilinear transformation always makes the number of zeros equal to the number of poles. And we can use the MATLAB command bilinear to transform this h continuous of s into h of z, to do these steps for us. So it goes like this. So we have a continuous time system, so we will define two polynomials. One is 5 and 10, which corresponds to the numerator polynomial, something like this. So I will define c equal to 5 and 10, and d, which will be the polynomial of the denominator, 1, 7, and 12. Here we have 1, 7, and 12. So first let's check where are the pools located. So the pools of the continuous time system will be roots of d. So we have two pools at -4 and -3. Both of them are located in the left half plane. Now let's use the bilinear transformation. We have a command called bilinear cd, and here we give it the value of td, which is 2 in our case, and now we get the two polynomials. A is the numerator polynomial and B is the denominator polynomial. And as you can see over here, the numerator is 0.75, 1, and 0.25. As you can see over here, 0.75, 1, and 0.25. And the denominator is 1, 1.1, and 0.3. 1, 1.1, and 0.3. So the command actually performs the bilinear transformation for us. One difference though, here I'm using GNU Octave. It takes the value of TD, so this 2 is the value of TD. Where in MATLAB, it might ask you for the value of 1 over TD, which is 0.5. That's why in the command here in the slides, we have 0.5, not 2, because in MATLAB, it asks for 1 over TD, whereas in Octave, it asks for TD as it is. So let's check if the pools of the discrete time filter are located inside the unit circle, because this was one of the features we need to have. So now we know that we have two pools of the continuous time system at -4 at -3, located in the left half plane. So the pools of the discrete time system would be like this, roots of B. So -0.6, -0.5, both of them are located inside the unit circle, which tells us that the bilinear transformation actually maps the left half plane of the S-domain inside the unit circle. Any pools happening in the left half plane will be mapped inside the unit circle. Okay, so let's talk about the properties of this bilinear mapping or bilinear transformation. So the equation we have is that S is equal to 2 over TD 1 minus Z minus 1 over 1 plus Z minus 1. And we will try to get Z as a function of S. So S times TD over 2 times 1 plus Z minus 1 will be equal to 1 minus Z minus 1. Then we will try to bring Z minus 1 together. So we will be having Z minus 1 times 1 plus S TD over 2 equal to 1 minus S TD by 2. And now we can write Z as follows: 1 plus S TD over 2 over 1 minus S TD by 2. Or we can multiply by 2 over TD in the numerator and the denominator, we will get this form. Now we can replace S by sigma plus j omega. So Z will be equal to 2 over TD plus sigma plus j omega over 2 over TD minus sigma minus j omega. But don't forget, Z is R e to the power j omega. Therefore, we can find the relation between R and lowercase omega and sigma and uppercase omega as follows. These equations can be found very easily. The one thing to note over here is that if sigma is less than 0, if sigma is negative, which corresponds to the left half plane of the S domain, if sigma is negative, you can see that the numerator will be less than the denominator, which means R is less than 1. In other words, the left half plane of the S domain is mapped inside the unit circle. And if sigma is equal to 0, this means that the numerator and denominator are equal to each other, which means R is equal to 1. In other words, the j omega axis itself is mapped on the unit circle. And if sigma is larger than 0, which corresponds to the right half plane of the S domain, you will find out that the numerator is larger than the denominator and R would be larger than 1. And these three properties are very important. They map the left half plane inside the unit circle, j omega axis on the unit circle, which guarantees that a causal and stable continuous time system is mapped to a causal and stable discrete time system. So, if sigma is less than 0, R is less than 0, and the left half plane of the S domain is mapped inside the unit circle. And if sigma is equal to 0, R will be equal to 1, and the j omega axis will be mapped on the unit circle. And if sigma is larger than 0, R would be larger than 1, and the right half plane will be mapped to the outside of the unit circle. Therefore, a causal and stable continuous time filter will be mapped into a causal and stable discrete time filter. In other words, the bilinear transformation preserves stability. Okay, so as you can see, we have talked about this mapping before. What about the frequency? The j omega axis over here is extending from minus infinity up to positive infinity. How come it's mapped only on the unit circle? So let's see. If S is 0, sigma plus j omega, 0 plus j 0. Let's go back to the equation we have over here. If we set sigma to be equal to 0 and omega capital to be equal to 0, R will be 1, and omega small will be 10 minus 1, 0 minus 10 minus 1, 0, which is 0. So R equal to 1, omega is equal to 0. So as you can see over here, S equal to 0 is mapped onto this point. Magnitude 1 and frequency 0. What if omega goes to positive infinity? If omega goes to positive infinity, you will get to this angle omega small equal to pi, and if omega capital goes to minus infinity, you will go again to pi or minus pi, which are equivalent to each other. Going back to the equations over here, if you set omega capital to infinity Again, the numerator and denominator will be equal to each other, and r will be equal to 1, so you're still in the unit circle. And if you check the frequency over here, tan minus 1 infinity is pi by 2 minus tan minus 1 minus infinity, which will give you minus pi by 2. So omega will be pi, which is clearly seen over here. If s is equal to infinity, we will be having capital omega equal to pi, and if s is equal to minus infinity, we will be having omega small equal to minus pi. So, since the continuous time frequency axis j omega is mapped onto the discrete time frequency circle e to the power j omega, we can derive the exact relationship between capital omega and lowercase omega by setting sigma equal to 0. Because the j omega axis is the continuous time frequency, it's happening at sigma equal to 0, we can set sigma equal to 0 in the relation between lowercase omega and uppercase omega. This equation over here, if we set sigma to be equal to 0, we will get a relation between omega small and omega capital. And this relation will take this form. Omega small is equal to 2 tan minus 1 omega td over 2, or capital omega is equal to 2 over td tan minus 1 omega by 2. From which we can see that if capital omega is 0, lowercase omega is 0. If capital omega goes to infinity, omega small goes to pi. If capital omega goes to minus infinity, omega small goes to minus pi. So the entire j omega axis in the s domain is mapped onto the unit circle. And this means we do not have aliasing in frequency. This point would have been made more clear if we have talked about the impulse invariance transformation. In the impulse invariance transformation, we have aliasing happening. Here we do not have aliasing. But for now, let's just skip this part. So, the positive j omega axis in the s domain is mapped onto the upper unit circle from 0 to pi, and the negative j omega axis in the s domain is mapped onto the lower unit circle from 0 to minus pi. And as you can see over here, we have a highly nonlinear relation between lowercase omega and uppercase omega. And this nonlinearity imposes some critical restriction on the use of bilinear transformation. So we have a tan minus 1 relation between lowercase omega and uppercase omega, and this nonlinear relationship is known as a frequency warping, which basically means that the bilinear transformation converts the continuous time transfer function we have into a discrete time transfer function by compressing the continuous time frequency range, which goes from minus infinity to positive infinity, onto the unit circle, which goes from minus pi to pi. And the next figure will help us understand the situation and understand the implications happening. So, this is a nonlinear relationship between lowercase omega, the discrete time frequency used, and uppercase omega. As you can see over here, the curve is almost linear up to 0.3 pi. Therefore, if we have a linear response happening over here in the continuous time, it will be mapped into a linear response in the discrete time due to the approximately linear transfer function between capital omega and lowercase omega. But for larger values of lowercase omega, we will be having nonlinear relation. Therefore, if we have this flat response over here extending from 1 up to 3, it will be mapped into a wider response in the discrete time. So the frequency has been kind of expanded. But the response will be flat even though we have non-linear relation, because again it will be compressed or expanded. But if we have a linear response happening at higher frequencies, due to this non-linear relation, we will get non-linear response, besides the compression or expansion happening in the frequency domain. So, we note that for lowercase omega less than 0.3 pi, the relation between capital omega and lowercase omega is approximately linear. And therefore, any shape of magnitude response in this range is preserved, linear or flat. And frequency warping does not distort flat magnitude responses because any rearrangement of equal values will preserve the flatness of the shape. Thus, equirable bands are mapped into equirable bands. But the frequency warping distorts non-flat magnitude responses if the frequency omega small is larger than 0.3 pi. Hence, the bilinear transformation should not be used to convert filters with non-flat magnitude response, because if we have a non-flat magnitude response, it will be distorted, as we can see over here. If we have a linear, which is non-flat response, it will be mapped into a non-linear response. It will be distorted. Also, the frequency warping distorts the location of frequency bands and their widths. As we can see over here, this band extending from 1 to 3 was kind of expanded or extended in the discrete time frequency range. And this band extending from 4 up to 7, it has been kind of compressed. So the frequency warping distorts the location of frequency bands and their widths. Thus, to design discrete time filter with specific omega k, we need to determine the design specification for the continuous time filter by first pre-warping the frequencies, according to this relation we have between capital omega and lowercase omega. So, the subsequent application of the bilinear transformation will unwarp the frequencies to the correct specification omega k, in which we have omega k is equal to 2 tan minus 1 omega k Td by 2. The consecutive application of pre-warping and warping during the design process will cancel the effect of Td, thus we are free to choose any value for Td. The phase response of a continuous time filter will be affected in a similar manner, but we will ignore the phase response for now. So, the bilinear transformation is appropriate for filters which has piecewise constant magnitude response or flat magnitude response, because flat responses will be mapped into flat responses in the discrete time, such as low pass, high pass, and band pass filter. But the bilinear transformation does not preserve responses with linear magnitude or linear phase characteristics. It will be distorted, the linear phase or linear magnitude. So, the design procedure goes as follows. In order to design a digital low-pass filter with this kind of specification, omega s, omega p, AP, AS. First step, we'll let Td equal to 2. Second step, we will pre-warp the frequencies we have, lowercase omega p, lowercase omega s to uppercase omega p and uppercase omega s, using the equation we have, omega p equal to tan omega p small over 2 and omega s equal to tan omega s over 2. This is a pre-warping step. Then we need to design a continuous time filter with omega s, omega p, AP, and AS. And now we can apply the bilinear transformation, which will shift the location of frequencies omega p capital, omega s capital, into omega p and omega s lowercase, which we already want. So here we have an example. We need to design a second order Butterworth digital filter with a cutoff frequency of 2 kHz and a sampling frequency of 20 kHz. So we can use the prototype Butterworth filter we have seen in the previous lecture, which has a cutoff frequency of 1 radian per second. And for a second order filter, it will have the form 1 over s squared plus square root 2 of times s plus 1. Next, we need to find the cutoff frequency of the digital filter. So we need to design a digital filter whose cutoff frequency is equal to capital omega c over sampling frequency, which is 2 pi times 2k over 20k, which will give us 0.2 pi. So the objective is to design a digital filter whose cutoff frequency is 0.2 pi. But keep in mind, we have a highly nonlinear relation between lowercase omega and uppercase omega. So in order to have the digital filter with a cutoff frequency 0.2 pi, we need to pre-warp omega c first using this equation 2 over TD tan omega c over 2, which will give us a cutoff frequency for the continuous time filter of 0.32492. Now designing a second order Butterworth filter with this cutoff frequency and then applying the bilinear transformation will give us a discrete time filter whose cutoff frequency is 0.2 pi. So in order to design the second order Butterworth filter with this cutoff frequency 0.32, we need to replace every s with s over omega c prime. So replacing every s with s over omega c prime, we will get this expression. Next, we need to use a bilinear transformation by replacing every s by z minus 1 over z plus 1, or replacing every s by 1 minus z minus 1 over 1 plus z minus 1, which will give us this transfer function over here. It's a second order numerator over a second order denominator, so we have 2 pools and 2 zeros. And again, the number of pools is preserved. We had a second order continuous time filter, so we have here a second order discrete time filter, but the number of zeros has been changed. In the continuous time filter we had no zeros at all, but the discrete time filter will have 2 zeros.